up to this point, all the graphs that we have dealt with have not had asymptotes in them. So our job now is to kind of finally put everything together. All the things we know about end behavior and asymptotes, all those things are going to be a thing, okay? So it will still, the stuff we learned in pre-calc, now we just can verify more algebraically than we ever could before. So let's just talk about what limits to infinity are. Yeah. So if we look at the limit to infinity here, so this one would be the limit as we approach infinity. It is heading to a height of 2. But to negative infinity, we are also heading to a height of 2. So this would be written as the limit as x approaches infinity of f of x is equal to 2. And this would be written as the limit as x approaches negative infinity of f of x also equals 2. So limits to infinity. So limits to infinity are notation we touched upon a little bit last year when we were talking about end behavior. Let's talk about why this goes to, as we go to infinity, why does it go to 2? So if we look at our function, as we go to infinity, anytime we have a fractional function where our x's in our denominator are higher than the x's in our numerator, it's always going to head to 0. So this piece heads to 0, but we're always adding on 2. And so that's what happens. This becomes, it's heading to 2 plus 0. This is heading to 2 plus 0. And the further we go out, the further it would, or the closer it would become to 2. So that's why that one happened. Now we're going to explore those rules as we go through this process. So remember, this is just the notation for right end behavior. This is the notation for left end behavior. So if we look at this graph, that is heading to the right end is heading to some height of L. This left end is heading to some height of M. So I guess we could say for our left end one, let's make that an M. Let's make that an M, because we're actually heading to a height of M. I don't know why they changed the letter and didn't change that. But. So remember, a horizontal asymptote, it's what are you approaching if you're approaching a height on the ends. Horizontal asymptotes are a little funky. We can cross them. Vertical asymptotes we can never cross, but a horizontal asymptote, you might bounce over it for a little while before you actually come back down. And we can see that in a function like the cosine of x over x plus 1. You can see that we are actually on the right end heading to a height of 1. Now, not on the left end, but on the right end, we are heading to a height of 1. So it has a horizontal asymptote at 1. But you see that it crosses it multiple times. Now, it keeps getting closer and closer and closer. So you could possibly cross a horizontal asymptote, but you're never going to cross a vertical asymptote. So be careful of that. If your graph ends up crossing it, but you come back down to it, that's okay. Okay. There's some new rules that we're going to need to know. One that's really important is called L'Hopital's rule. That isn't La Hospital, it is L'Hopital. And L'Hopital's rule basically says that if you get 0 over 0, or if you get infinity over infinity, then if you take the derivative of each your top and bottom function, you can try the limit again. So this is just a really cool way to verify what you're getting. So remember before we've got that 0 over 0. And I always say, well, you know, use the coefficients on the x's. Well, here, if we do derivatives, we can actually get it to the point where we can clearly see what the limit is. So L'Hopital's rule is going to be one that's helpful. Here's something that's really important. If we have a 1 over x to the n and n is greater than 0, then the n behavior is always 0. So the n's go to 0. Okay, so if you have 1 over x to the n and n is any positive number, so 1 over x to the 1/2, 1 over x to the 3rd, 1 over x to the 5th, the n's will always head to 0. So that's just an important thing. And then if f of x is a polynomial, the limits to infinity are just the n behavior. Use the lead term in the term that we know. So if it's an x cubed, you know, one arm's up, one arm's down. If it's an x squared, they're both going to go up or they're both going to go down. So some of these things we already know. We might not have called them a particular terminology. So when we're in pre-calc, we pretty much called them n behavior. What are the n's doing? What are the horizontal asymptotes doing? Well, now we're going to use that limit notation. But L'Hopital's rule just gives us something to do if we get 0 over 0 or infinity over infinity. Try to take the derivative of each and try it again, and something sometimes will happen. This theorem just tells us it's always going to go to 0. This tells us that the limits to infinity, you just can use the n behavior based upon the lead term. So those are just some rules that are pretty important that we're going to use as we go through this process. So let's just take a look at these particular problems. It says determine the horizontal asymptotes or the n behavior for these functions. So let's look at this first one. So first let's do the limit as x approaches infinity. So remember, that's just the right end. Now we learned about limits, that for limits, we could take the limits of the individual terms. So the limit of a constant, whether we're going to a number or infinity, always goes to that constant. That's something we learned about limits. So that goes to 5. This limit uses that theorem I was talking about before. The power in the denominator is x squared, so that one goes to 0. That one has a horizontal asymptote at 5. Now, if we do the left end behavior, if you square a negative, it's still going to become a positive, but it's still going to head to 0. So it's still doing 5 plus 0 or 5. Now, if we look at the graph of that, you can see that our left end and our right end are both heading to a height of 5. So we have a horizontal asymptote for both ends at y equals 5. So example A has a horizontal asymptote at 5. Now let's take a look at B. And let's look at the right end. So as the sign goes to infinity, the sign is going to wobble, okay? So this one is one of the most unique cases that we look at. For this one, where is the sign at any particular spot as we go out to the right? Well, it's some number between +1 and -1, who knows, you know, it's just going to keep going. So this one, we can't use L'Hopital's rule, it doesn't help us. Instead, we just have to know, and this is a rule that we might eventually add on to our cards, that this always goes to 0 for both the left end and the right end. So it is just kind of a rule that we're going, there's no real, there's a proof of it. It's very kind of convoluted and weird, but that's just one that you want to memorize. Okay, so if we look right here, this is what the graph does. And so it's kind of acting like a sine wave, but we're going to keep dividing by something bigger and bigger and bigger and bigger. So that +1 and -1 keeps being divided until it gets smaller and smaller and smaller. And so that's kind of what's happening. I mean, if you kind of think about this is always between 1 and -1, and then we're dividing by that x, it kind of somewhat follows that rule that we know about that 1 over x to the n. Okay. But C is a little nicer. I would pull the 4/3 away from that because we know that this is heading to 0 and a limit, any constant we can pull out in front. So that's just 4/3 times 0 or 0. So guess what? As we go to -infinity, that's just 4/3 times 0 again. So it has a horizontal asymptote at 0. You could even write this one, there's a horizontal asymptote at 0. So here's the graph of 4 over 3x. See how our end behaviors go to 0. So there is a horizontal asymptote at 0. But I've always taught you in pre-calc and in the beginning of the year when we reviewed graphing stuff, that if our power in our denominator is bigger than our power in our numerator, it's going to go to 0 anyway. But now we have some theorems that go with that. And then I would like to do D. D is a candidate for L'Hopital's rule. Now let's talk about why. If you think of plugging in infinity, and well, we don't really do that, but a very, 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 very large number, wouldn't the top go to infinity, right? And the bottom would go to infinity. So this is a perfect candidate for L'Hopital's rule. And this is how easy L'Hopital's rule is. What is the derivative of 5x minus 1? Yeah. What is the derivative of 3x plus 2? 3. What is the limit of a constant? A number? A constant. So the answer is 5/3. So L'Hopital's rule is really nice for polynomial functions because as they go to infinity or negative infinity, it works for either one, you can use L'Hopital's rule. So that is our right end behavior goes to 5/3. The same rule would apply for the left end behavior because the top will go to negative infinity and the bottom will go to negative infinity. Negative infinity over negative infinity is a candidate for L'Hopital's rule. What's the derivative we just found? Same derivative. So it'd be 5/3. The derivative, or I'm sorry, the limit of a constant is just the constant. So that goes to 5/3. 5/3 is about 1.7. And you can see here that is 5/3. So that one has a horizontal asymptote on both ends of 5/3. Now there are some functions where the left end will actually have a different horizontal asymptote than the right. Most of the time, both ends will go to the same sort of thing. So that is limits to infinity. End behavior, end behavior, end behavior. What are the ends doing? So there's lots of different tactics that we're going to use. You know, it just depends upon the function, okay? Let's think of a polynomial. We haven't had one that's just a polynomial. When I see limits to infinity of a polynomial like x cubed, we know that x cubed looks like that. There should be no hesitation as to what an x cubed looks like. So we know that the limit to positive infinity of x cubed goes to positive infinity. The right end goes up. The left end goes down. Even if it was x cubed plus 2x plus 7, doesn't matter. The lead term is x cubed, the left end goes down and the right end goes up. Guess I could put it on the actual graph paper. Okay. The left end goes down and the right end goes up. That should not be a shock to you. Polynomials are wonderful. We know lots about what is happening to them. So there shouldn't be any surprises there, okay? So end behavior, only one of three things is going to happen. The ends might approach some horizontal asymptote of L. The ends could go to infinity. Or we might not have a limit to infinity because the function doesn't exist there, like a square root. So remember, if you're taking a limit to infinity, you're just doing end behavior. It's either going to give you a height, it's going to go to plus or minus infinity, or it might not exist. Those are the only three options you have for those questions. So just contemplate what are you looking at? And what do we know about those sorts of things? Okay. Fractional functions tend to either go to a height of something, 0, or maybe a fraction, depending on what the coefficients are. So fractions do tend to go to something. You know, you just got to explore, and then we have some of those tools we can use. Remember, if it's an even power or an even polynomial with a lead term that's even, so the lead term both ends are going to go up or both ends are going to go down. So your limits to positive infinity and negative infinity will always match. If the lead term has an odd power on it, the limits to infinity will be the opposite. One will be positive and one will be negative, depending upon what we know about that particular function. So you know the end behavior of polynomials. Base it upon the lead term, because the lead term tells you all you need to know about the ends. Doesn't tell you where the bumps are in the middle. We know how to find the bumps in the middle now using first derivative test and second derivative test. So we're starting to know so much more about functions and how to show them algebraically than we did in pre-calc. So let's take a look at this. It says for each, we're going to find the end behavior. So let's take a look at A. For A, we know that it is a flipped upside down power function with an odd power. So we know that A looks something like that. It's a flips upside down cubic with a negative exponent. It's going to flip it upside down. That 5 is just going to kind of stretch it. But so the left end goes to positive infinity, but the right end now goes down. So the left end's going to go up. That should be of no surprise. Let's think about function b, 2x to the 4th. 2x to the 4th looks something like that. Why? Well, it's an even power. It's going to look like a parabola. That 2 in front stretches it, but it doesn't flip it or anything. So this is going to go to positive infinity because the right end is going to go up. The left end behavior is also going up. So the limit as x approaches negative infinity of 2x to the 4th is also positive infinity because the left end is going up. At this point, those should not be anything magical. You should know that. And it's just notational now. Recognizing that a limited to infinity is saying what's the right end doing, a limit to negative infinity is what's the left end doing. So just knowing that those are referring to end behavior. So what's the picture looking like? What do I know about that sort of polynomial, and what can I do about it? So that should not be, anything that doesn't surprise you, okay? Okay. Now, let's take a look at some of our rational functions, our fractional functions. Let's take a look at A. So if we do the limit to the right, which is the limit to infinity, if you think about plugging in infinity, you get infinity over infinity. So rational functions, that's a nice L'Hopital's rule. So if I took the derivative of that, you just take the derivative of the top and the bottom, I get 3 over 2. So the answer is 3 over 2. The same thing happens for this one. If you do negative infinity, you get negative infinity over negative infinity, which is a L'Hopital's rule candidate. So I can do the derivative of the top and the bottom. I get 3/2, and the derivative of a constant is that constant. So if you were to graph it, both ends are heading to a height of 3/2. But we learned last year if the power on top and the power on the bottom match, that we are allowed to use the coefficients on the x. I didn't tell you that those coefficients appear because of our rules of derivatives and things like L'Hopital's rule. Yeah. So if you could still do it, you can still do L'Hopital's rule. It can be either positive or negative infinity. instead of 3/2, we might get a negative 3/2. And there are some times where the because of the way our power rule and things work, that you might end up with your negative infinity goes to a positive, but your positive infinity goes to a negative. They can go to different things. It doesn't always happen, but it is possible. Okay. So if we look at B, our higher power is in our denominator. Right now, if we try to do the limit to infinity, I'm just going to put an F there to be a little lazy. If we do the limit to infinity, we do still get, and here's a case, Levin, where we get positive infinity over negative infinity. If you think about, oh no, we will for the negatives, but the positive, we get positive infinity over positive infinity, which is a L'Hopital's rule candidate. If we take the derivative, though, what do we get? We get 6x plus 2 over 12x squared minus 5. I should have put that in front. Okay. If we plug in infinity, we still get infinity over infinity. So we can do it again. And then we get 6 over 24x. And we can't do the infinity over infinity anymore, right? 6 is not infinity. But we learned something earlier about, did I do the derivatives right? Just tell me, did I do the derivatives right? Okay. But we do know something about that type of function. 6 over 24 is really 1/4. So let's kind of separate the 1/4 from the 1 over x. What does 1 over x always go to? 0. So this is 1/4 times 0 or 0. Now back in pre-calc and at the beginning of this course, I always told you if the higher power is in the denominator, we are always going to head to 0. So if you look back at the original, isn't the highest power in our denominator? We're going to head to 0. So that's going to be true for both our left end and our right end. They're both going to head to 0. And that's what this graph right here is showing us. The left end and the right end are both heading to a height of 0. It is a funky graph. Okay, and then our last one here, we have, for the first time, the higher power in our numerator. Now, we did not deal with these much last year. I talked about it maybe a little bit, and then we kind of probably skimmed across it, and we kind of just probably moved on. If the higher power on top is exactly 1 degree higher than the bottom, we are going to follow what's called a slant asymptote. If the higher power on the top is more than 1, it ends up kind of acting like a polynomial in a way, the ends do. So this is exactly 1. So this is going to have what's called a slant asymptote. Okay. Now initially we can still do the L'Hopital's rule. We can actually do L'Hopital's rule, and we can take the limit of the derivative of it, because we're going to positive infinity over positive infinity. If you do the derivative, you get 6x plus 4 over 1. And that tells us that our limit to infinity is just the limit as x approaches infinity of the polynomial 6x plus 4. Now that's a line. A line is 6x plus 4 is a slope with a positive line. I mean, the A line with a positive slope. So on the right side, isn't it just going up to infinity? So the answer is infinity. If we use the same rule for L'Hopital's, negative infinity goes down to the left because that line would slope up. Okay. But how do we find the line that is actually approaching? So we know that it's heading to positive infinity and negative infinity, and that's what the graph tells us. But let's talk about how we actually find that slant. How do we find that slant asymptote? To find a slant, you have to use long division. I know, that's gross, isn't it? You have to use long division. No. So we're going to do 3x squared plus 4x divided by x plus 2. You have to use long division. Okay, so we're going to use long division. So what would you multiply x by to get 3x squared? 3x. Then we're going to multiply. We're going to get 3x squared plus 6x. Then we're going to subtract. We get negative 2x. What would we multiply x by to get negative 2x? Negative 2. There's your slant. You don't have to do anything further. As soon as you get to that constant, you're done. So our slant is the line y equals 3x minus 2. Do you see right here? That's the line that that graph is following. Y equals 3x minus 2. Okay, so we are going to talk about slants a little bit more. Let's do one more, and then we're going to stop. It says find the limits for a kind of, it's called a transcendental function because it's got e's on top and bottom. It's got irrational numbers in it. Okay. So if we look at going to infinity, we are going to get infinity over infinity. E to the x goes to infinity for both the top and the bottom. Okay. So if we do L'Hopital's rule, would you agree that we are going to get the derivative of an e to the x is an e to the x? I don't think that graph is right. Anyway, which is 3/5, and I think the answer is, oh, I'm sorry, negative. I think the answer is negative 3/5. But let's do the math here. Where do I get an E? Would I put exponential? No, I don't know. What do I put? Okay, we'll get E. Oh, okay. Shoot. Yeah, I couldn't do that again if I tried. Shoot. I'm so sorry. Be quiet. Okay, wait, how did I get the E? And how do I get a keyboard? Okay. Functions.
You would have to have it in full screen. You go into functions, you go into exponential, you subtract some letters.
I did.
There you go.
There is a much easier way to do it.
It's so much easier. It's so entertaining though.
Okay, so the right end is definitely heading to -3/5. Is the left end? Because it looks like it's going to 0.
Oh, by the way, in order to get the keyboard, you just press the ABC button in the bottom.
Oh, okay. Okay, I'm sticking by the answer is -3/5, but I'll get back to you. Okay. Anyway, so these limits to infinity, they should not to be something that takes you forever, because you should just start recognizing what some of the rules are. And we'll go over some of these tomorrow. But your 4-6A homework is what you see there.